Let's review a couple previous theorems before doing the divergence theorem. Green's theorem gives us a way to convert between the line integral of a 2D vector field along a closed curve to a double integral over the region inside the curve using the derivatives of the vector field. Similarly, Stokes' theorem lets us convert between the line integral of a 3D vector field along a closed curve to a double integral over a surface bounded by the curve using the curl of the vector field, which can be viewed as a derivative for the vector field. If we close up the surface from Stokes' theorem and consider the outside surface versus the region inside the surface, we get the divergence theorem. Let me state this precisely. Let E be a simple solid region. Simple means that E has no holes, so it's not like Swiss cheese. Let S be the boundary surface of E, given with positive, meaning outward, orientation. Let F be a vector field whose component functions have continuous partial derivatives on an open region containing E. The surface integral of f along S, meaning the flux of f across S, is equal to the triple integral over E of the divergence of f. Let's talk about what this means physically. If f represents the velocity field of a fluid flow, the flux computes the net rate that the fluid is crossing S. Recall that the divergence computes at each point if the point is a source for the fluid flow. So what this triple integral does is it adds up all the sources for the fluid flow inside the region E, and this is equivalent to computing what's happening on the boundary of E. This theorem is very nice because it can allow us to bypass computing a surface integral and do a triple integral instead. Here's an example. Suppose we want to use the divergence theorem to compute the surface integral of f across S, where f is the positively oriented surface of the solid bounded by the paraboloid z equals x squared plus y squared and the plane z equals 4, and f is the vector field given here. As always, we should draw a picture. I'm going to draw my surface S. S is a paraboloid that's capped off at z equals 4. We can describe the solid region E as z going from x squared plus y squared to 4, and x and y bounded by the disk of radius 2. It's looking like cylindrical coordinates will be useful here, so let's represent the solid in cylindrical coordinates as z bounded below by r squared, above by 4, r running from 0 to 2, and theta running from 0 to 2 pi. If we want to use the divergence theorem, we'll need the divergence of f. This is computed as the partial derivative of each component with respect to the variable in that component added up. So we get the partial derivative of cosine of z plus x times y squared with respect to x, the partial derivative of x times e to the minus z with respect to y, plus the partial derivative of sine of y plus x squared times z with respect to z, which comes out to y squared plus x squared. This is great because my integrand is way simpler. So the divergence theorem says that instead of computing that ugly surface integral, we're going to compute the triple integral of the divergence of f over e, which means that we're integrating just x squared plus y squared over e, which in cylindrical coordinates becomes r squared times dz dr d theta, where z runs from r squared to 4, r runs from 0 to 2, and theta runs from 0 to 2 pi. This comes out to 32 pi over 3.